Welcome back, everyone. Today, in this explainer, we're embarking on a journey straight to the absolute limits of physics. We're going to explore the universe's most enigmatic objects, black holes, and we're going to do it without getting completely bogged down by dense differential geometry. We are focusing entirely on the foundational model that really started it all, the Schwarzschild Black Hole. Together, we're going to get a crystal clear picture of what actually happens when gravity just completely overpowers the fabric of space and time. So let's get started. But to truly appreciate this science, we first have to appreciate the absolutely incredible human history behind it. Back in 1915, Albert Einstein published his general theory of relativity, and almost immediately, a German physicist and astronomer named Carl Schwarzschild found the very first exact solution to Einstein's incredibly complex equations. But here is the truly astonishing part. He did it while serving on the Russian front in the brutal trenches of World War I, all while suffering from a fatal autoimmune disease. He actually wrote this beautifully haunting line in a letter to Einstein just shortly before he died. "The war treated me kindly enough to allow me to take this walk in the land of your ideas." It's just wild to think that out of the total horrors of war came the mathematical birth of the black hole. Okay, let's dive into this. What exactly did Schwarzschild discover? Well, it's known today as the Schwarzschild radius, and thanks to something called Birkhoff's theorem, we know that this math actually describes the gravity outside of literally any spherically symmetric non-rotating object. That means this very same math applies to our sun, and hey, even the Earth. But it only actually creates a black hole if an object's entire mass is compressed completely inside this specific critical radius. If it crosses that threshold, the escape velocity exceeds the speed of light itself. To really wrap our heads around this, let's scale things down for a second and look at just how extreme this compression has to be. If you wanted to turn our entire planet Earth into a Schwarzschild black hole, you would have to crush all of its mass, every ocean, every mountain, every continent, down into a tiny sphere with a radius of just 8.9 millimeters. That is roughly the size of a standard glass marble. Now compare the Earth's tiny radius with our sun's. The sun is, of course, over 300,000 times more massive than the Earth. But to cross that threshold of no return and form a black hole, you would have to compress that gigantic, raging star down to a radius of just 3.0 kilometers. It's a level of density that completely defies human intuition.
So the crucial takeaway here is that a black hole's mass directly and linearly dictates the physical size of its event horizon, its Schwarzschild radius. On the top end of the scale, we have supermassive black holes. These are millions to billions of times the mass of our sun, with radii that can literally stretch across entire solar systems. Then down at the bottom, we have theoretical micro black holes, which could have the mass of our moon, but a radius of just a fraction of a millimeter. Basically, the more massive it is, the larger the sphere of darkness it casts.
Section 1. The bald black hole. Understanding the no-hair theorem. Let's see how this builds into the actual physical properties of these objects. This brings us to the famous no-hair theorem, and exactly why physicists jokingly refer to this model as bald. You see, if a complex object like a star collapses, it sheds almost all of its identifying features. The Schwarzschild black hole is literally the simplest model in the universe. It is defined by one thing and one thing only: its mass. It has absolutely no spin and no electric charge. Now compare that to real-world black holes, which likely do spin, something we describe with the Kerr metric, because of the conservation of angular momentum from the original stars that formed them. Some might even have a charge, which we model as Reister-Nordstrom or Kerr-Newman black holes. But to really grasp the extreme physics at play, we always start with a beautifully simple, non-rotating Schwarzschild model. Section 2. The journey inward, crossing the event horizon.
So what actually happens if you get too close to one? We're going to shift our narrative right now to a bit of a thought experiment, taking a journey inward to explore the extreme physics right at that boundary of no return. Imagine an observer watching a hapless companion falling toward a black hole. Step by step, it gets pretty grim. Because of severe gravitational time dilation, the outside observer sees their falling friend's actions become increasingly, agonizingly slowed down. Their image becomes increasingly redshifted as the light desperately struggles to climb out of that deep gravitational well, eventually just fading to black. But for the falling friend, well, they are experiencing extreme tidal forces. The gravity at their feet is so much stronger than at their head that they are violently stretched and torn apart, a horrific process physicists actually colloquially call spaghettification.
But hey, let's say our friends somehow miraculously survived crossing that null surface of the event horizon. This is where reality truly bends. Outside the horizon, time moves relentlessly forward, but you can move freely in space. Inside the horizon, though, the causal structure of space-time actually flips. The radial direction of space and the forward direction of time literally swap roles. The center of the black hole is no longer a physical place in space, it is a moment in your future. Moving toward the center is as inevitable as tomorrow. You simply cannot go back.
And that inevitable future brings you exactly here, the singularity. At radius equals 0, all that mass is crushed into an infinitely dense point. The mathematical curvature of spacetime actually diverges to infinity. It's a really profound moment in this explainer because this is where we just have to admit defeat. Our current understanding of physics, Einstein's general relativity, entirely breaks down at this true singularity. To understand what happens here, we would need a unified theory of quantum gravity, which, honestly, we just don't have yet.
Section 3, Shadows and Real Detections, proving the math.
Now you might be wondering, if not even light can escape and the center is entirely hidden from the outside universe forever, how do we know this isn't all just a mathematical fantasy? Well, that massive gravitational pull curves spacetime so severely that it forces light rays to bend entirely around it. Light that gets too close is captured by the horizon, creating a very dark, distinct shadow against the glowing gas behind it. And this brilliantly illustrates exactly how we do it. Through the incredible, groundbreaking work of the Event Horizon Telescope, we've actually imaged the shadow of the supermassive black hole in galaxy M87. By measuring the exact size and shape of this shadow, astronomers can confirm the predictions of general relativity and rule out alternative models of gravity. Schwarz's century-old math perfectly predicts the very shadows we see through our best telescopes today.
Section 4, The Ultimate Quantum Mystery, where general relativity meets quantum mechanics. So, we have established the classical mechanics, but our story definitely doesn't end there. We need to introduce one final, totally mind-bending concept that pushes the absolute boundaries of modern astrophysics and actually touches the quantum realm. It turns out, black holes aren't entirely black forever. Thanks to the legendary work of Stephen Hawking, we know that when you add quantum mechanics into the mix, the event horizon isn't perfectly dark. Over extremely long timescales, black holes emit a faint thermal glow called Hawking radiation. And because they are actively radiating away energy, they are slowly, inevitably losing mass. Given enough time, we're talking trillions upon trillions of years, a black hole will slowly evaporate away into absolutely nothing. Which leaves us with arguably the biggest unresolved mystery in all of physics. If a black hole evaporates completely, leaving behind only a featureless thermal bath of radiation, what happens to the highly detailed, pure quantum information of everything, every star, every planet, every hapless companion that ever fell inside? If that information is truly lost forever, it is a shocking violation of quantum unitarity, which is a core pillar of quantum mechanics itself. Does the information somehow escape? Is it destroyed? Or is there just something fundamentally wrong with how we understand reality at its core? I want to leave you pondering that question today. Thank you so much for joining me on this deep dive into the dark heart of the universe. Keep looking up and definitely keep asking questions.